Welcome to today's explainer. Okay, so today we are going to play a little game with numbers. And look, I want you to completely forget all that scary, stress-inducing math you might have learned in school. Just toss it out. Instead, I want you to imagine that you have this magical toy box. You take a giant, heavy, incredibly frustrating math problem, you drop it inside, you turn the little crank, and out pops a tiny, easy puzzle that honestly a 4-year-old could solve. That magic box, it has a name. It's called a logarithm. Now, to really appreciate this magic box, imagine having to count every single star in the sky, or maybe every grain of sand on a beach, completely by hand. Hundreds of years ago, before calculators were a thing, people literally had to multiply giant numbers like 237 and 481 using just a feather pen and paper. I mean, it took absolutely forever. And the worst part? One tiny mistake in your carrying or borrowing and the whole thing was ruined. They desperately needed a shortcut. And you know what? That shortcut is exactly what our magical box does. Instead of doing that hard, messy multiplication by hand, you just drop those big, clunky numbers into the translator, and it magically turns them into simple, relaxing addition. It's basically like taking a massive, chaotic construction project and turning it into just clicking 2 Lego blocks together. That's the secret. Multiplication simply becomes addition. So, let's actually look at how this works, taking it in really tiny steps. Our magic box is completely obsessed with the number 10. All it's doing is asking a very simple question. How many times do I multiply 10? Or, if you want an even easier way to think about it, how many zeros are there? Let's look at the number 10. It has 1 0, right? So its magic number is 1. The number 100 has 2 zeros, so its logarithm is 2. 1,000, 3 zeros, so it's a 3. You are quite literally just counting the zeros. Okay, let's prove our first magic rule with a micro example here. Normally, if you take 10 times 100, you get 1,000, right? But in our new magic language, the number 10 turns into a 1, and the number 100 turns into a 2. So you just add those together. 1 plus 2 is 3. And as we just saw, 3 is the exact magic number for 1,000. So that hard multiplication, it literally just turned into 1 plus 2. How cool is that? Now, this magic, it goes both ways. Think about it. If multiplication becomes adding Lego blocks together, what do you think division becomes? Exactly, it becomes subtraction. You're just taking the blocks apart. So 1,000 divided by 100 is 10. But in our magic language, you just take the 3, subtract the 2, and you're left with 1. And yep, 1 is the magic number for 10. It just flows so beautifully. All right, here is the third trick, and this one is a real game changer. Dealing with giant powers, say 100 to the power of 3, is usually like trying to build a tower to the moon. It's a million. But pass it through our magical box, and those scary powers just become basic multiplication. You just take that power of 3 and multiply it by the magic number for 100, which is 2. 3 times 2 is 6. And guess what? The logarithm of 1 million is 6. We literally just shrank a million into the number 6. And finally, we have the fourth trick, roots. Now, finding a square root by hand is, well, it's a giant headache. Nobody wants to do that. But in our magic language, roots just mean chopping things in half. For the square root of 100, we just take its magic number, which is 2, and simply divide it by 2. 2 chopped in half is 1, which again is the magic number for 10. It really is like actual magic. But wait a second, I know what you're probably thinking. We've only been using perfect, round numbers with zeros so far. What about the messy, everyday numbers? Well, to handle those, we just split our translated number into 2 friendly little pieces. We have the characteristic, which is just a fancy way of saying the big whole number part, and then we have the mantissa, which is an even fancier word for the tiny decimal pieces left over. Let's test this out. If we put a messy number like 389.4 into our box, out pops 2.59040. Now, don't let that big long string of numbers scare you. Just mentally snap it right in half. That 2 in the front, that's our big whole number, the characteristic. The 59040, those are our tiny leftover pieces, the mantissa. And why is that big number a 2? Well, because 389 lives between 100 and 1,000. It's in the hundreds, so it belongs in the 2 zeros family. Now, I want to show you a really fun game that I like to call the decimal point dance. Take a really close look at this list of numbers. Do you notice a pattern here? Whether it's 349,000 or 0.349, the actual core digits never ever change. It is always 3496. Literally, the only thing moving around is that little decimal dot. And here is why this is so unbelievably cool. Because those core digits stay exactly the same, the tiny decimal pieces of our magic number, the mantissa, they stay exactly the same too. Look at that. Every single one ends in 54357. The only thing that actually changes is the big number in front, which just kind of counts up like a staircase as that dot moves to the right. Because of this trick, people hundreds of years ago only had to memorize the tiny pieces. The big numbers just sort themselves out. Okay, but what happens when numbers get smaller than 1? This is where people usually get a bit confused, but honestly, it's just like walking down a set of stairs into a basement. We know the log of 10 is 1. The log of 1 is 0. So what happens if we step down one more time into decimals? We just walk right into negative numbers. 0.1 is -1. 0.01 is -2. You're just walking backward. But we do run into a tricky little problem here. If we have a tiny, messy number, its whole translated magic number would become a grumpy negative decimal, and that makes the math hard again, which defeats the whole purpose. So the old mathematicians invented something called the bar trick. By putting a little line over the 3, almost like a little magic hat, it tells us that only the 3 is negative. The tiny decimal pieces on the right, they get to stay happy and positive. Even with the magic hat, some people really hated playing with negative numbers at all. So they came up with another clever little loophole. They just gave the numbers a secret booster pack. If a number was, say, -2.4, they would artificially add 10 to it right at the start, turning it into a bright, positive 7 point whatever. It was basically a game to keep all the numbers looking nice and positive on paper, and then they just subtract the 10 at the very end. And let me tell you, this booster pack trick was an absolute lifesaver when it came to chopping tiny numbers in half, like when finding a square root. Think about it. If you have a -3, you can't chop it evenly in half without breaking your happy positive decimal pieces into messy fractions. So they made up a rule. First, give it a giant booster pack of 20. Boom! Now you have a nice big positive number. Second, you just chop that evenly in half. Problem totally solved. Once you grasp that little game, this next trick is going to make perfect sense. If you need to find a cube root, well, you have to chop the number into 3 pieces. So, to make sure everything chops evenly and stays beautifully positive, what booster pack do you think we use? Right, the magic number is 30. You just add 30, divide it evenly by 3, and you get your answer without dealing with a single grumpy negative fraction. Now, let's tackle one of those scary-sounding math phrases, the arithmetic complement. I know it sounds like some brutal college exam topic, but I promise you, it's literally just a toddler's game of make 10. That's it. It just asks one simple question. How much do I need to add to get to 10? If you have a 2, you need an 8. If you have a 4, you need a 6. It's seriously that easy. So why on earth was this childish game so useful to grown mathematicians? Because it magically turned subtraction into addition. Instead of doing all that annoying borrowing and carrying by hand just to subtract, you can just add the make 10 number instead, and then drop the extra 10 at the end. The whole system was all about finding these clever little loopholes to make math as painless and relaxing as possible. So, stepping back, all of these strange tricks we've covered, the whole numbers, the tiny pieces, the magic hats, the booster packs, they were all just tools to help operate this magic box. If you remember absolutely nothing else from this explainer, remember these 4 rules of our magical translator. Multiplication becomes addition, division becomes subtraction, powers become multiplication, and roots become division. The math literally just takes one giant step down in difficulty across the board. Our source material actually summarizes this whole journey beautifully. It says, that's the magic of logarithms. Hard multiplication becomes easy addition. You see, logarithms were never, ever meant to make school harder for you. They were a brilliant, incredibly elegant game invented entirely to make impossible math doable for regular human beings. We've seen today how translating numbers into a totally different language can turn a grueling, brain-melting task into child's play, which kind of leaves us with a pretty incredible thought to chew on. If a simple, magical translator can make impossible math easy, what other incredibly complex problems in our lives, in our businesses, or in our world are actually quite simple? We just haven't found the right magic box to put them in yet. Something to think about, right? Thank you so much for joining me for this explainer, and I'll catch you next time.